Hello and welcome back to our TAE certification training series. In this session, we will be going through the last three approaches, which are keyword-driven testing, process-driven scripting, and model-based testing. Today's session is going to be a bit lengthy, but trust me, it's jam-packed with valuable insights. So now that we are done with the intro, let's begin. Okay, so let's start with keyword-driven testing. The keyword-driven scripting technique builds on the data-driven scripting technique. There are two main differences. The first one is that the data files in the data-driven testing are now called test definition files or something similar, for example, action word files. And the second difference is that there is only one control script. A test definition file contains a description of the test in a way that should be easier for test analysts to understand, easier than the equivalent data file. So we'll see it in a while. It will usually contain data, as does the data files, but keyword files also contain high-level instructions, the keywords or action words. Okay, so here is an example of a data file in CSV format. A data file typically contains raw data that specifies the inputs required for a test. So in this data file, we have rows of data where each row represents a set of test inputs, in this case, username and password. As you can see, the file contains no instructions or keywords. So test analysts need to rely on external documentation or knowledge to understand how to use this data in test cases. Now let's have a look at an example of a test definition file. A test definition file combines data and high-level instructions within the same file. In this test definition file, you have a combination of keywords, for example, open browser, login, and associated parameters, for example, URLs, usernames, passwords. Each row represents a step in a test case. In this case now, the test analyst can easily understand the flow and purpose of each step by reading the keywords. This makes it more user-friendly and eliminates the need for external documents. Okay, also let's have a look at this keyword param1, param2. These represent the header row that defines the structure of the file. It specifies the format in which the test steps should be organized within the file. You must have noticed that in front of open browser there are two commas. So in the test definition file, this indicates that this keyword function, open browser, it does not require any parameters to be passed to it. So the first comma is a placeholder for the first parameter, which in this case is not used. It is there to maintain consistency in the structure of the test definition file, because open browser is a keyword that initiates the opening of a web browser. Same goes with the second comma as well. That's also a placeholder for the second parameter, which is also not used. The same applies to close browser keyword as well. Okay, so let's go ahead with the further concepts of keyword-driven testing. The keywords should be chosen to be meaningful to the test analyst, the test being described and the application being tested. Okay, so if we again have a look at this test definition file, over here, open browser, navigate to website, and login and close browser, they all are keywords which are chosen to represent specific actions to be performed during the test. These keywords are chosen to be meaningful and describe high-level interactions with the system under test. For example, open browser signifies the action of starting a web browser. Okay, let's go ahead with the other point. These are mostly but not exclusively used to represent high-level business interactions with the system. For example, place order. Each keyword represents a number of detailed interactions with the system under test. For instance, login keyword represents the action of logging into a website. So these keywords guide the detailed interactions within the test cases. For example, the login keyword specifies that the test should enter a username and password and click the login button. Next, we have sequences of keywords including the relevant test data are used to specify the test cases. So sequences of these keywords along with the relevant parameters are used to specify test cases. In the file, a sequence of keywords is used to describe the steps to perform a login operation for multiple users. Special keywords can be used for verification steps, or keywords can contain both the actions and the verification steps. Okay, while our example over here, it does not include verification keywords, we could add them to verify successful logins, for instance. Okay, then we have the scope of responsibility for test analyst includes creating and maintaining the keyword files. This means that once the supporting scripts are implemented, test analyst can add automated tests simply by specifying them in a keyword file, as with data-driven scripting. Okay, so when test analysts need to create a new test case or modify an existing one, they can simply update the test definition file with the appropriate sequences of keywords and parameters to describe the test steps. So the underlying supporting scripts they remain unchanged. So test analysts can concentrate on the test case logic rather than the scripting details. With this approach, the process is very simplified of creating and maintaining tests, making it accessible to test analysts without extensive technical expertise. Okay, so over here we have an example, the same login process example, but now we have a keyword-driven script. The code begins by importing the required libraries, including CSV for reading test data from a CSV file and WebDriver from Selenium for browser automation. Next, we have a series of functions which are defined, each representing a specific keyword that can be used in test cases. So first of all, we have Open Browser. This function initializes a Chrome web browser instance and returns it. Next, we have Navigate to website. So given a browser instance and a URL, it navigates the browser to the specified URL. Then we have Login. This function simulates the login process by finding web elements for username, password, and submit button, and then filling in the provided username and password. And then at the end, we also have close browser, and this function closes the browser when called. Then an instance of the Chrome browser, web browser is initialized using the open browser function, and it's stored in the browser variable. Now over here, the script reads test steps from a CSV file named login_test.csv. The CSV.reader is used to read the file, and over here the next reader is called to skip the header row. Right, okay, now over here the script enters a loop. If you can see, it's a loop over here to process each row from the CSV file, where each row represents a test step. The keyword variable stores the keyword for the current step. Depending on the keyword value, the script calls the corresponding function to perform the associated action. For example, if the keyword is open browser, it calls open browser function to open a new browser instance. If the keyword is navigate to website, it calls navigate to website function to visit the specified URL. Same if the keyword is login, it calls login function to simulate a login action. And in the last, if we have close browser, if the keyword is close browser, then it calls close browser function to close the browser instance. So now, as we have gone through the entire code, I would like to highlight one more thing over here. In the earlier example of the data-driven testing, so if you go back to the script, the login script which we had for data-driven testing in our last session, the browser was opened at the beginning of the script and closed at the end. So I want to explain that, like, why we did differently in that one than this one. Okay, so over there, why we opened at the beginning of the script and closed at the end, because it was intended to execute a series of test cases sequentially, with each test case having its own set of login data. Opening and closing the browser once ensured that each test case started with a fresh browser session and didn't have any dependencies or side effects from the previous test cases. However, in this example, in the keyword driven example, the script is designed to be more modular, and this allows for more flexibility in structuring test cases. So the browser is open and closed within certain keyword functions such as open browser and close browser. So this allows us to define more complex test scenarios where we might want to open the browser at the beginning of a test case, perform multiple actions, and then close the browser within that test case. So the choice of whether to open and close the browser at the beginning or at the end of the script or within individual test cases, it all depends on your testing requirements and the structure of your test scenarios. In keyword driven testing, you have more control over when the browser is opened and closed, making it suitable for a wider range of testing scenarios. Right, okay, now let's move on to the next slide. And now we have some pros and cons for keyword driven testing. The first advantage is cost efficiency. Once the controlling script and supporting scripts for the keywords have been written, the cost of adding new automated tests will be much reduced by this scripting technique. This means you can create new tests without incurring significant additional expenses. The second one, freedom for test analyst. Having the test described by the keyword files means that test analysts can specify automated tests simply by describing the test using the keywords and associated data. This gives test analysts more freedom to specify automated tests without as much dependency on the technical test analyst, who may be a scarce resource. If you would go back to the data-driven testing advantages, you would notice that these two are similar. Now we'll move on to the third one, which is different. High-level actions. The benefit of the keyword-driven approach over the data-driven approach in this regard is the use of the keywords. Each keyword should represent a sequence of detailed actions that produce a meaningful result. For example, open browser, login, close browser are all high-level actions in our login script. When one test analyst describes a system test to another test analyst, they are likely to speak in terms of these high-level actions, and this allows tests to be defined in terms of the high-level actions without reference to the detailed steps. Another advantage is abstraction and maintainability. These test cases are easier to maintain, read, and write, as the complexity can be hidden in the keywords or in the libraries in case of a structured scripting approach. The keywords can offer an abstraction from the complexities of the interfaces of the SUT. For example, the open browser keyword takes care of initializing the browser and navigating to a specific URL. The exact WebDriver commands and settings are encapsulated within this keyword. Similarly, the login keyword abstracts the detailed steps of locating username and password fields, entering credentials, and clicking the login button. Okay, now let's have a look at some disadvantages. So the first one is implementation overhead. Implementing the keywords remains a big task for test automation engineers, particularly if using a tool that offers no support for this scripting technique. For small systems, it may be too much overhead to implement and the cost would outweigh the benefits. Okay, so in our keyword driven testing script, which we just had a look, each keyword, like open browser or login, corresponds to a specific action. So implementing these keywords, especially if you are using a tool without built-in support, it can be a significant task for test automation engineers. Next, we have keyword selection. Care needs to be taken to ensure that the correct keywords are implemented. Good keywords will be used often with many different tests, whereas poor keywords are likely to be used just once or only a few times. So, example for good keywords, open browser and login. And so why these are good keywords? Because you will likely use them more frequently in various tests. And let's have a look at an example of poor keywords. So there can be a keyword like perform unique login for this particular test. It might only be applicable to one specific test case, making it less valuable in the long run. Okay, so now we are done with the keyword driven testing and let's move on to process driven scripting. Process driven scripting is an approach that's like an advanced version of keyword driven scripting. Instead of keywords, we create specific scripts for different scenarios in our system. In our login example, it involves creating scripts for different scenarios related to logging in. These scripts are like sets of instructions for various situations such as a successful login or a failed login attempt. We can customize these scripts with specific test data or combine them into larger test definitions. Okay, so for instance, one script might be for a regular login, while another script could be for handling forgotten passwords. So these scripts are easier to manage because we can clearly see the logical order of actions like entering credentials before clicking the login button. This approach helps us thoroughly test different aspects of the login process. Okay, so now here is an example of a process-driven script for a login scenario. That's the CSV file known as login_process. Okay, so in this example, we have two scenarios. Scenario one is successful login and scenario two is invalid login. Each scenario consists of a series of steps that represents actions performed during the login process. The steps include actions like opening the browser, navigating to the login page, entering a username and password, clicking the login button, and verifying the results. So depending on the scenario, different parameters are used. You can create a script to read and execute these steps one by one, following the defined process. So this allows you to easily parameterize scenarios and test different cases without writing separate scripts for each. Okay, now the key advantage of process-driven scripting is that it provides a structured way to define and execute scenarios, which makes it very, very easy to manage and maintain test cases for different test scenarios or use cases of your application. Now let's have a look at the pros and cons for process-driven scripting. The first one is workflow perspective. The use of process like scenario-based definition of test cases allows the test procedures to be defined from a workflow perspective. In other words, it enables you to structure your test procedures based on how tasks flow within a particular scenario or use case. Then we have high-level workflows. The focus of process-driven scripting is to implement high-level workflows. These workflows are typically represented by sequences of actions or steps that need to be performed during testing. So for the login scenario, this means you can define a sequence of actions such as navigate to login page, enter credentials, and authenticate as part of the login process. Then we have test libraries. To implement these workflows, process-driven scripting often utilizes test libraries. These libraries contain predefined, reusable test steps or actions that correspond to detailed interactions with the system under test. In the login example, a test library may contain predefined, reusable test steps like enter credentials or authenticate user, making it easier to construct and maintain your login test cases. Let's have a look at few cons now. The first one is complexity for technical test analyst. Processes of an SUT may not be easy to comprehend by a technical test analyst, and so is the implementation of the process-oriented scripts, particularly if no business process logic is supported by the tool. So in the context of the login process, creating a process-driven script might involve defining intricate workflows that represent states like logged out, login page, entering credentials, authentication, and logged in. So for a technical test analyst who is not well versed in the details of the login process, understanding and implementing these workflows can be complex. The next one is correct process implementation. Care needs also to be taken to ensure that the correct processes by use of correct keywords are implemented. Good processes will be referenced by other processes and result in many relevant tests, whereas poor processes will not pay off in terms of relevance, error detection capability, etc. Okay. So if we take the login example again, when defining the login process, it's essential to choose the correct processes and keywords. For instance, the correct sequence might involve navigating to the login page before entering credentials and authentication. So if these processes are not implemented accurately, it can lead to very ineffective test cases. And a well-defined login process should be referenced by other processes to create relevant tests. However, if the processes are poorly designed or irrelevant, they will not contribute effectively to error detection or test relevance. Now coming to our last approach, model-based testing. Model-based testing refers to the automated generation of test cases. See also the model-based tester syllabus by ISTQB, which itself is another certification, as opposed to the automated execution of test cases by use of capture/playback, linear scripting, structured scripting, data-driven scripting, or process-driven scripting. Okay, so model-based testing uses semi-formal models which abstract from the scripting technologies of the TAA. Different test generation methods can be used to derive tests for any of the scripting frameworks discussed before. Let's have a look at this diagram. In model-based testing, the focus is on creating models that describe the behavior of the system under test rather than writing detailed scripts. So these models are typically semi-formal, meaning they provide a structured representation of the system's behavior, but not at the level of detail that you would find in a scripting language. So the key idea is that model-based testing abstracts away from the technical intricacies of traditional scripting methods. It is a high-level approach that allows you to describe what the system should do in a more intuitive and abstract way using models, rather than specifying exactly how it should be done through code. Different test generation techniques can then use these models to automatically generate test cases for the system, making the test process more efficient and less reliant on manual scripting. Okay, here's the information presented in a tabular form for the application of model-based testing to our login example. Okay, so we have different stages and description. The first one is model creation. In the context of the login example, create a model that represents various states and transitions within the login workflow. Abstract the technical details and focus on the logic of actions. For example, logged out, login page, entering credentials, authentication, logged in. The next one is automated test case generation. Utilize MBT tools or techniques to automatically generate test cases based on the defined states and transitions in the model. Test case examples. So let's have a look at the few examples of the generated test cases. Test case 1. Start from logged out, navigate to login page, enter valid credentials and reach logged in. Test case 2. Start from logged out, navigate to login page, enter invalid credentials and stay at login page. Next, the last stage is test execution. Execute the generated test cases automatically, similar to traditional test automation. Okay, so this table provides a simplified workflow of how model-based testing can be applied to our login example, from model creation to test case generation and execution. Okay, so now let's have a look at few advantages and disadvantages. The first advantage, abstraction focus. Model-based testing allows by abstraction to concentrate on the essence of testing in terms of business logic, data, scenarios, configuration, etc. to be tested. If we think about our login example, this means concentrating on the key steps involved in logging in, abstracting away all the technical details. The next one is future safe representation. It also allows generating tests for different target systems and targeted technologies so that the models used for test generation constitute a future safe representation of testware which can be reused and maintained as the technology evolves. So in the login example, this implies that the model for the login process can be reused and maintained even as the underlying technology evolves. For instance, if the login page design changes, the model can be updated and new test cases can be generated accordingly. Then we have automatic test case generation. In case of changes in the requirements, the test model has to be adapted. Only a complete set of test cases is generated automatically. Test case design techniques are incorporated in the test case generators. In the login example, if new login requirements are introduced, you can modify the model and the testing tool generates the relevant test cases. Okay, let's have a look at some disadvantages. Modeling expertise. Modeling expertise is required to run a model-based testing approach effectively. The task of modeling by abstracting an SUT's interfaces, data, and/or behavior can be difficult. In our login example, creating a model that accurately represents the login process might require specialized knowledge. Next, maturing tools. Modeling and the model-based testing tools are not yet mainstream, but they are maturing. This means that there might be limitations in available tools and techniques when applying model-based testing. The tools and methodologies may not be as mature or user-friendly as traditional testing tools. Process adjustments. Model-based testing approaches require adjustments in the test process. For example, the role of test designer needs to be established. So, and this individual would need expertise in modeling techniques, which might not even be a requirement in traditional testing. Then we have major artifacts. The models used for test generation constitute major artifacts for quality assurance of an SUT and need to be quality assured and maintained as well. Okay, so this means that the models created for generating test, they play a significant role in ensuring the quality of the system under test. They need to undergo quality assurance processes and be regularly maintained to ensure they remain effective in producing reliable test cases. Okay, so for this one, we have covered uh, all the approaches. So we have explored a range of powerful approaches, and now it is time to bring it all together and answer the million-dollar question. Which test automation approach should you choose? So before we proceed with this, I just want to clarify that this summary on this slide, it's not part of this syllabus. However, I have included it because I believe that a well-rounded understanding of these approaches empowers you to make informed decisions and then adapt to real-world testing scenarios. Because whatever we are studying here, it's not only for the certification. Of course, you should be able to apply in your real life as well. So it is all about giving you the tools and knowledge to think critically and then choose the right approach for your project. Okay, so let's just have a look. The first one is capture playback approach. So if you are looking for a quick and simple way to get started with test automation, especially for smaller projects or when time is of the essence, the capture playback approach might be your go-to. It's very user-friendly and it requires minimal coding skills. Then we have linear scripting. For straightforward linear test scenarios where the test flow is simple and does not change frequently, linear scripting can be a reliable choice. It's great for automating repetitive tasks. Then we have structured scripting. When your test scenarios are a bit more complex and require better organization and maintainability, structured scripting comes to the rescue. It provides a systematic approach to test automation. Next, we have data-driven testing. If you need to run the same test with multiple sets of data, data-driven testing is your best friend. It's excellent for testing various inputs and conditions systematically. Next comes keyword-driven testing. When you want to separate test logic from test data and create reusable test components, keyword-driven testing shines. It's perfect for enhancing test maintainability and scalability. Process-driven scripting. In cases where your tests mimic real user interactions with complex workflows, process-driven scripting can accurately replicate those scenarios. It's ideal for end-to-end testing. And the last one, model-based testing. When you are dealing with complex systems or intricate requirements, model-based testing provides a structured way to create and execute tests which are based on system models. It's perfect for ensuring comprehensive coverage. Now remember, there is no one size fits all answer. The choice of test automation approach depends on various factors, including project size, complexity, available resources, and also your team's expertise. And before making a decision, evaluate your specific testing needs and consider the pros and cons of each approach. Sometimes a hybrid approach combining elements from different methods can be the most effective. In the end, the goal is to maximize test coverage, maintainability, and efficiency. So go ahead, testers, armed with this knowledge, and choose the test automation approach that suits your unique project testing. Happy testing, and I will see you in the next session. Thank you.